Hello everyone, my name is Dr. Raj Dandekar. I graduated with a PhD in machine learning from MIT in 2022, and I am the creator of the Build DeepSeek from Scratch series. Before we get started, I want to introduce all of you to our sponsor and our partner for this series, invideoAI. All of you know how much we value foundational content, building AI models from the nuts and bolts. InVideo AI follows a very similar principle and philosophy to that of us. Let me show you how. So here's the website of InVideo AI. With a small engineering team, they have built an incredible product in which you can create high quality AI videos from just text prompts. So as you can see here, I've mentioned a text prompt, create a hyper realistic video commercial of a premium luxury watch and make it cinematic. With that, I click on generate a video. Within some time, I am presented with this incredible video, which is highly realistic. What fascinates me about this video is its attention to detail. Look at this. The quality and the texture is just incredible. And all of this has been created from a single text prompt. That's the power of NVIDIA's product. The backbone behind the awesome video which you just saw is NVIDIA AI's video creation pipeline, in which they are rethinking video generation and editing from the first principles. To experiment and tinker with foundational models, they have one of the largest clusters of H100s and H200s in India and are also experimenting with B200s. InVideo AI is the fastest growing AI startup in India, building for the world. And that's why I resonate with them so much. The good news is that they have multiple job openings at the moment. You can join their amazing team. I am posting more details in the description below. Hello, everyone, and welcome to this next lecture in the Build DeepSeek from Scratch series. For a quick recap, here is what we have covered so far. We are on our journey to understand multi head latent attention, and up till now, we have understood self attention. We covered this module from basics and also the coding part of this. We understood causal attention in the previous lecture, and today we are going to understand the fundamentals of multi head attention. In the next lecture, we are going to code multi head attention, but today, the main thing which I want to convey to you is what is the real need for having this multi-head attention, and why can't we just stick with causal attention, let's say. The more I read in literature and the more resources I've seen, very few people have explained what is the real need for having multiple heads in attention. So, without going into the code or without directly jumping into the code first, it's very important for us to develop a very strong intuition of why we have multiple heads. So, today's lecture is titled Going from Self Attention to Multi Head Attention. And I'm going to try to explain this to you in a very intuitive manner directly from the first principles. So, let's get started with today's lecture. As we have seen before, the main goal of the self attention mechanism is essentially to take input embeddings and to transform them into something which is called as context embeddings. Remember that input embeddings on their own do not contain any information about neighbors. So, for example, if I look at a single token in a sentence, input embedding captures the semantic meaning of that token and its position, but it does not capture how that token relates to the other tokens in the sequence. And that's the additional mechanism which self attention brings into the picture. The context vector, which is the main outcome of the self attention mechanism, contains information of how a given token attends to all its neighboring tokens. And to go from the input embedding matrix to the context embedding matrix, we have essentially four parts. The first part is transformation to query key value matrices. Second part is calculation of the attention scores. Third part is calculation of the attention weights. And fourth part is the context vector matrix calculation. So let's quickly see these four parts in action right now. So let me take you to that part of the notebook where we did those calculations. Here it is. So here's the input embedding matrix which we have. There are one, two, three, four, five tokens, and each token is essentially an eight-dimensional vector. In the first step, what we do is that we multiply this input embedding matrix with trainable query, key, and value weight matrices, and then we get this query vector matrix, the key vector matrix, and the value vector matrix. After this point, we forget about the input embedding matrix completely and only operate on these queries, keys, and the values. That's step number one. Step number two is we take a product of queries multiplied by the keys transpose. And that essentially gives us the attention scores. So every row of this corresponds to the attention score of that particular token. So for example, the second row of this matrix corresponds to the attention scores for next, and how next actually relates to the next day is bright. So these five attention scores are mentioned in this or are calculated in this second row. Similarly, all other rows have attention scores of that particular token. The main drawback of attention scores is that the rows don't sum up to one. So we cannot make intuitive claims that when next is the query, give 10% importance to the, give 50% importance to next, etc. So to do that, we have to normalize the attention scores. And we have two steps in the normalization. First, what we do is that we take the attention scores and we divide them by the square root of the keys dimension. This is done so that the variance of the queries multiplied by the keys transpose, that stays equal to 1 and the variance does not become too large. And then we apply the softmax function. The softmax essentially ensures that when you look at a particular row, all the entries of that row will sum up to 1. So this is normal self attention where we look for a given token, we look forward as well as backward. In the causal attention mechanism, what we do is that all the elements essentially above this diagonal, all of these elements are essentially put to zero, because for a given token we should not have access to all the tokens which come after that particular token. So all of these elements which I've marked in the green color right now, they are effectively masked to zero. That's what happens in the causal attention mechanism. And then we can apply dropout to the attention weight so that we randomly mask out some elements to be zero. This is to improve the generalization performance and to prevent overfitting. The last step which is done here is that we take the attention weights matrix and we multiply with the value matrix to give us the context vector matrix. And here you can see that every row of the context vector corresponds to my token. So the first row is the context vector for the second row is the context vector for next, etc. And if you look at the visualization of the context vector, you'll see that the context vector is much richer because it takes into account how much attention is paid to all the nearby or the neighboring tokens of next, for example, whereas the input embedding does not have that richness in information about the neighboring tokens. So this was in a nutshell the self-attention mechanism and the causal attention mechanism also. Remember that when we saw the causal attention mechanism, what we essentially did was we we put the all the elements of the attention weights above this diagonal to be equal to zero, and then after that we can also add dropout. So we can further randomly turn off certain attention weights to zero. That was causal attention. Okay, so with that, let's get started with today's lecture in which we will motivate why do we need to go from self attention to multi head attention. So, first, remember that self attention is awesome and self attention has a lot of advantages because we finally start including or encoding information about the context which is present in the given sentence. Without self attention mechanism, language models would not be as good as understanding the meaning of sentences as they are today. But for all the advantages of self attention mechanisms come with one very major problem, and multi attention solves that problem. So let's see what this problem with the self attention mechanism is. And for that, I want to start out with a simple illustration. So, what I want to start out with is that I want to start out with a sentence, right? And the sentence is The artist painted the portrait of a woman with a brush. Let me read this sentence aloud once more. The artist painted the portrait of a woman with a brush. Now, try to think about what do you think this sentence means. You can pause the video for a while and think about the interpretation of this sentence. Okay, so if you have thought for some time, you will have realized that the reason I have chosen this sentence is that it has two interpretations. The first interpretation is that the artist, so let's say if this is the artist has painted the portrait of this woman using a brush. So the artist painted the portrait of a woman with a brush, which means that the artist had a brush in their hand, and with that the artist painted the portrait of a woman. That is the first interpretation. The second interpretation is that the artist painted the portrait of a woman with a brush. So the painting is of a woman who has a brush in their hand, and the artist has painted this. So you see the difference. In the first case, the painting is that of a woman who does not have a brush in her hand. The artist is painting the portrait with a brush. But in the second case, it's the painting or the portrait of a woman with a brush in their hand. So this is the painting. So this is a woman with a brush in her hand, and the artist has painted this. So the first is a painting a woman with a brush, and the second is painting of a woman with a brush, right? So these are the two interpretations of this sentence. The problem of the self attention mechanism comes into the picture over here. So what I want to now do is that I want you to focus on two attention scores matrices, and which I'm going to uh, put them together side by side over here now. So take a look at the attention score matrix number 1, and so take a look at attention score number matrix number 1 and matrix number 2. And what I'm also going to do is that I'm going to bring these corresponding images below it. Okay, so this is the first image, and then I'm also going to bring the second image now. Here, I've brought the second image now, and let me just rub this arrow. Okay, now I want you to focus on these two attention score matrices. Okay, the first attention score matrix, which I've marked here as number 1, it corresponds to this image, right? And why is that? Because focus on the woman. If the woman is my query, the circles which I've marked in the red here correspond to the highest or the strongest attention scores. So you can focus on those red circles for now. So here we have a red circle between woman and a portrait. Since it's a portrait of a woman, the attention score between woman and portrait is quite high. That is understandable. Whereas if you see over here in the second attention scores matrix, the attention score between woman and the portrait is still high. That is understandable because here also we have a portrait of a woman. But notice this red color over here. The attention score between woman and the brush is also very high. And why is the attention score between woman and the brush also high? Because in the second interpretation, the woman is holding a brush in her hand. That is the difference between this row in the first attention score matrix and this row in the second attention score matrix. In the second attention scores, the attention score between woman and the brush is quite high, whereas that's not the case in the first attention score, because in the first attention score matrix the woman is not holding a brush in her hand. The second distinction which we see is when we look at essentially artist. So when we look at artist, in the first matrix, the artist has a high attention score with painted, and the artist has a high attention score with brush. Why? Because the artist is holding a brush in her hand in the first interpretation. Whereas if you look at the second interpretation, If you look at the second interpretation, the artist is actually not holding a brush in their hand, and that's why the attention score between artist and the brush is actually not very high. That's the second difference between these two attention score matrices. And the third difference between these two is when you look at brush. So when you look at brush, you'll see that the attention, if brush is the query, it has high attention scores with artist because the artist is holding the brush, and it has high attention scores with uh, what is this? It, yeah, this should not be there. So the brush just has a high attention score with the artist because the artist seems to be holding the brush, right? Whereas here, if you see, brush has a high attention score with portrait because the portrait is that of a woman with a brush, and brush also has a high attention score with woman. Why? Because the woman has a brush in her hand. So brush has a high attention score with portrait and woman in this case, whereas in this case brush has a high attention score with artist. So I hope I have convinced you now that in these two interpretations of the sentence, the attention scores matrix are completely different from each other, right? There can be two attention score matrices based on the interpretation which you have for the sentence. Now, the main problem with the self attention mechanism is that the self attention mechanism can only capture a single perspective in a given input sequence. It cannot capture multiple perspectives. So, if you are looking at this sentence, the self attention mechanism will either have this attention scores matrix or it will have this attention scores matrix. And consequently, the context vector will either be based on the first attention score matrix or the second attention score matrix. So it cannot take into account both of these perspectives at the same time. And that's one major limitation of the self attention mechanism, that if you are given a piece of paragraph or a piece of sentences, self attention can only capture one perspective. So if you think about it more deeply, why would you want to capture multiple perspectives in a sentence? The reason you would want to capture multiple perspectives in a sentence or paragraph is that sometimes it is difficult to understand uh, what the paragraph represents in just one form or meaning. One paragraph might have different angles, right? One paragraph might be expressed in multiple different ways. And when we design our language model, we want our language model to be knowledgeable of multiple different perspectives present within a paragraph. An example here is that, let's say we have a huge paragraph, right? And within that paragraph, we have a sentence which reads like this: the government should regulate free speech. Now, if you look at this sentence, the government should regulate free speech, the first perspective should be the government should impose restrictions on free speech. So, free speech should be curtailed. That's the first perspective. The second perspective should be the government should protect and preserve free speech. It's not really clear from this sentence which perspective is this paragraph referring to. So it just says regulate free speech. So regulating free speech can either mean that free speech should be curtailed or free speech should be protected and preserved. What does this line really mean? So if we use the self attention mechanism, again it will assign only one perspective to this. But we actually want the attention mechanism to capture both of the perspectives which this sentence can include. And the advantage of capturing both perspectives is that our model just becomes more richer in its understanding. So when a user asks to summarize this document, we can summarize both the perspectives. Whereas if we just use a self attention mechanism and a user asks to summarize this document, we will only summarize one perspective, and that is not good. So we want to overcome this limitation of self attention mechanism. So essentially, what we want to do is that we want to have provision in our model so that we can have, or we can capture different perspectives in my paragraph. So if one self attention mechanism can only capture one perspective, can we somehow extend the self attention mechanism so that it can capture multiple perspectives? So if one self attention mechanism can essentially just capture one perspective within the same architecture, what if I have multiple self attention mechanisms? What if I have multiple self attention mechanisms? So if one self attention mechanism can capture one perspective, multiple self attention mechanisms can capture multiple perspective. So if let's say one self attention mechanism gives me one context vector matrix, another self attention mechanism gives me another context vector matrix, a third self attention mechanism gives me a third context vector matrix, I'll have these multiple context vector matrices, each of which capture different perspectives, and then I'll just merge them together so that the final context matrix which I have will be much richer in that it will capture multiple perspectives of the given sentence or the given paragraph. So the main idea is this, right? You have instead of just having one self attention mechanism, what you can do is that let's say you have the input, uh, let's say you have the input embedding matrix, right? You pass it through self attention mechanism number 1, you pass it through self attention mechanism number 2. Let's say we look at 2 right now, so this will give me a context vector matrix 1, context vector matrix number 1, and this will give me a context vector matrix number 2. And then what I will do is that I will just merge these two context vector matrices together so that I'll have one resultant context vector matrix which now consists of multiple perspectives. This is perspective number 1 and this is essentially perspective number 2. And when I say perspective, it does not necessarily have to do with meaning always. It can be something else, like one context vector matrix essentially looks at or pays more attention to verbs in a given sentence. The second context vector matrix maybe pays more attention to the hidden meaning of a given sentence, etc. So multiple representations might come out from different context vector matrix. So here we are just trying to expand our range of what we capture from a given sentence. And this thing of converting the self attention mechanism to multiple self attention mechanism is essentially called as multi-head attention. Multi-head attention. The reason this term head comes into the picture is that it's essentially like having multiple self attention heads. So if you think of one self attention as one person with one head, it's like one head is giving one attention, right? But now you have multiple heads, each of these heads is capturing a different perspective. So think of these as multiple people. Let's say this is the first person with the first perspective, second person with the second perspective. So this is just a nomenclature, but the head comes from the fact that we are aggregating multiple self-attention blocks together, and that's where the name multi-head attention actually has its origins. Okay, so I hope until now I have motivated the concept of why do we need multi-head attention and what are the limitations of the self-attention mechanism. And now we are going to start looking at how does multi-head attention actually operate in the context of the matrices which we have seen before, the queries, keys, values, etc. How exactly can we change that whole procedure so that we have multiple heads? So the main question here right now is that what if we have two self-attention mechanisms instead of one? So let's take this same sentence. The artist painted the portrait of a woman with a brush. Now I'm going to show you the step-by-step procedure of how we can have two self-attention mechanisms within this sentence. And remember that the main purpose of this exercise is that if we have two self-attention mechanisms, we should have two attention scores matrices and we should have two context vector matrices because each has to capture a different perspective. So I'll need to show you how this is exactly done in the query key value representation which we have. Okay, so what if we have two self-attention mechanisms instead of one? Now, by the way, this two self-attention mechanism is also called having two heads, and that is the origin of the term multi-head. Okay, so now what we are going to do is that we are going to take this sentence and we are going to see a step-by-step procedure of how we can implement a two-head attention on this input sequence. And when you understand this step by step procedure, you will have a complete visual roadmap of how the multi head attention mechanism works. If you have understood self attention, multi head attention is actually quite straightforward. But I think in literature and in other videos, it just explained in a complicated and reverse manner. Instead, it's much easier to explain multi head attention if you motivate it like this. And then if you show the step by step visual matrix or visual matrices calculation. So let's see the step-by-step procedure right now. Okay, the first thing which we do is, as always, we start with an input embedding matrix, and the input embedding matrix looks like this. We have these tokens. The artist painted the portrait of a woman with a brush, right? We have these 11 tokens, and then every token is essentially uh, an input embedding of 8 dimensions, which we have considered over here. This is also called as the input embedding dimension, or DIN. So the dimensions of this entire matrix are, we have 11 rows and we have 8 columns. So the dimensions are 11 by 8. That's my input embedding matrix. Remember, the goal of this two head attention now is to take this input embedding matrix and to convert it into two context vector matrices, not just one. We have to convert it into two, so that each context vector matrix captures a different perspective. So this is the input embedding matrix which we have started with. And then the first thing which I want to do is show you what we would have done if we just had a single attention head. So if we have a single attention head, what would we have done? We would have multiplied this input embedding matrix with the trainable query matrix, which is an 8 by 4 dimension matrix, a trainable key matrix, which is an 8 by 4 dimension matrix, and a trainable value matrix, which is 8 by 4. And this multiplication would have resulted in a query vector matrix, that's 11 by 4, a key vector matrix, that's 11 by 4, and a value vector matrix, that's 11 by 4. Now, to extend this into a multi-head attention or a two-head attention in this case, what we have to do is that we have to first decide on the output dimension which we want. And here I am deciding the output dimension is equal to 4. That is something which is fixed at the start. The input dimension is fixed, the output dimension is fixed. Then what we do is that then we decide the number of heads which we want, and here we are having two attention heads, right? So this output dimension is then split among these two attention heads. So each attention head will have dimension equal to 2, and the way this visually looks right now is something like this. So now my trainable query key and the value weight matrices, earlier they looked like this, right? But now I'm just going to divide them into two parts. So my trainable query matrix is now, for the first attention head, it's this. So see, the size of this has been, now it's 8 rows and 2 columns instead of 8 rows and 4 columns. And for my second head, the trainable query matrix is this, which is again 8 rows and 2 columns. So in terms of nomenclature, now instead of WQ, I have WQ1, which corresponds to the first head, and I have WQ2, which corresponds to the second head. So if dimensions, understanding dimensions is a bit difficult, just remember that to split this into two attention heads, I've just divided the query into two parts, the keys weight matrix into two, and the value weight matrix into two. That's it. So this dimension over here, which the trainable query weight matrix has, the trainable query second for the second head, this is called as the head dimension. And the head dimension is just the output dimension divided by the number of heads. So the output dimension in our case is equal to 4, and the number of heads is 2. So the head dimension is just 4 by 2, which is equal to 2. So what is the head dimension? It's essentially the number of columns in each attention head, and that's equal to 2 in our case. And this same split happens for the trainable key matrix and the trainable value matrix as well. So similar to what we did for the trainable query matrix, we now have WK1, WV1, WK2, and WV2. So these are the trainable key matrices for the both heads, and these are the trainable value matrices for the both heads. So see, what we are doing in this step is that we are creating multiple copies of the trainable query weight matrix, the trainable key weight matrix, and the trainable value weight matrix. This is the main idea in the multi-head attention. And if you think about it, it's quite simple, right? In a single head, we just had one matrix. And remember that now that the d out is fixed, we cannot change this. So if we want two attention heads, we just split the d out into two parts. So these are my trainable query weight matrices, trainable key weight matrices, and trainable value weight matrices. That's step number 3. We essentially split or create multiple copies of WQ, WK, and WV. Now, now that we have multiple copies of WK, WQ, WK, and WV, it will naturally create multiple copies of the query vectors, the key vectors, and the value vectors, right? Because let's look at the query vectors first. I will first take my input embedding matrix X and I will multiply it with WQ1. So that's 11 by 8 multiplied by 8 by 2, and that will give me my first query vector matrix Q1, which is 11 by 2. Then I will take my input embedding matrix X and multiply it with WQ2. That will give me my second query vector matrix, that's Q2, which is again 11 by 2. Similarly, I take my input embedding matrix, multiply it with WK1 and WK2, and that gives me the two key vector matrices. And I take my input embedding matrix and I multiply it with WV1 and I multiply it with WV2. And then I get my two value vector matrices V1 and V2. Now remember here, what we have done simply is that instead of having one query vector matrix, one key vector matrix, and one value vector matrix for single head, since we have multiple heads now, we have two query vector matrices Q1 and Q2. We have two key vector matrices K1 and K2, and we have two value vector matrices V1 and V2. And what are the dimensions of these uh, these matrices? The number of rows essentially remain the same. So if you see, for all of them, the number of rows remains 11. Why do the number of rows remain 11? Because the number of tokens which I have, the artist painted the portrait of a woman with a brush, those are 11 tokens. But the key thing to note here is that the number of columns which we have, the number of columns now becomes equal to 2, because that's the head dimension. Remember, the head dimension is just the d out divided by the number of heads, which is equal to 4 divided by 2, which is equal to 2. So the number of columns in all of these matrices are equal to 2. Again, if you are getting confused, just look at the head number 1. All of these matrices are the query, key, and the value matrices for head number 1. And all of these matrices are the query, the key, and the value matrices for head number 2. Remember this, head number 1, we have these matrices, and head number 2, we have these matrices. It's just that we have now created multiple copies. So what happens is that we have the same vectors for a single head, but now we have two copies. And now that we have two copies, we still have only four dimensions, right? So each copy has to have only two dimensions. Remember, the d out is fixed at the start. So in step number 4, we create multiple copies of the query, the key, and the value vector matrices, which I have denoted over here right now: Q1, Q2, K1, K2, V1, V2. Now think about this, right? What is usually done in the next step? Usually we take the dot product of queries and the keys transpose to get the attention score matrix. But here we have two query matrices, we have two key matrices. So what will happen? Naturally, we will have two attention score matrices, right? So that's what happened next. We compute the attention scores for each attention head. So this is Q1, Q2, K1, and K2. So for computing the head 1 attention scores, what we simply do is we multiply Q1 with we multiply Q1 uh, with K1 transpose. We multiply Q1 with K1 transpose. So that's 11 by 2 multiplied by 2 comma 11, and that gives us the attention score of the first head. That's 11 by 11. Then what we do is that to find the attention scores matrix of the second head, we multiply Q2 with K2 transpose. So that's 11 by 2 multiplied by 2 by 11. That's 11 by 11. So now take a look here, what is exactly happening. When we looked at single head, if we look at a single head attention, we'll have an attention score matrix of 11 by 11, right? If we just look at one head, because there are 11 tokens here. The cool thing which has happened, or the amazing thing which has happened with multiple heads, is that although the output dimension is getting split into two parts, so the head dimension is equal to 2, the attention scores dimension remains the same for both the heads. It's 11 by 11 for the first head and it's 11 by 11 for the second head. and it would have been 11 by 11 if we just did a single head. So essentially now what we have done is that we have two copies of the attention scores. We have one 11 by 11 attention score and one 11 by 11 attention score. Why is it 11 by 11? Because remember there are 11 tokens, right? The artist painted the woman, painted the portrait of a woman with a brush, etc. And if you think about where we started with, this is exactly what we wanted, right? Instead of just getting one attention scores matrix, we wanted to extend the self attention mechanism so that we can get multiple attention scores matrices. And that is exactly what has happened here. Since we had two copies of the queries, since we had two copies of the queries and we had two copies of the keys, we can essentially multiply these two copies and get two attention scores matrices. So each attention score matrix essentially can capture a different perspective. And that's the main advantage of multi-head attention. This step here, that although we have multiple heads and although the dimension of each head is now split into two, so the head dimension is now equal to 2, which was 4 before. So in single head attention, it was 11 by 4 multiplied by 4 by 11. And that gave us the 11 by 11 attention score matrix. But now it's 11 by 2 multiplied by 2 by 11. So although this dimension is reduced by half, so although this dimension is essentially reduced by half, the final attention score matrix still is 11 by 11. So this dimension is same in both of these cases. That's the beauty of multi-head attention. Although each head has a reduced dimension, when we take the dot product of the queries and keys transpose for both the heads, we get two attention score matrices of dimensions 11 by 11, and each of these can now capture a different perspective. Essentially, we have two copies of the attention score matrices now. Then what happens in the next step? It's the same. Since we have two copies of the attention scores now, what we'll do is that we'll scale by square root of the keys dimension. We'll apply softmax, and then we'll apply causal attention, which means that we'll just make sure that all the elements above the diagonal are set to 0. Remember, we cannot peek into the future. And if needed, we can also apply dropout. So in this schematic, I've assumed the dropout rate to be 0, but after you get the attention weight matrix, you can even have a dropout rate and randomly turn off different elements in the attention weight matrix. So this is the head 1 attention weight matrix, that is 11 by 11, and this is the head 2 attention weight matrix, that is also 11 by 11 matrix now. And what is the difference between attention weights and attention scores? Attention weights, every row will just be normalized. So if you look at every row, it will be summed up to 1. And also remember that we are implementing causality here. So we make sure that for both of these attention weight matrices, the elements above the diagonal will essentially be equal to 0. So just keep that in mind. And then what we do in the last step is that now we have an attention head matrix for both these heads, right? And remember earlier we had calculated the value matrices v1 and v2. V1 was 11 by 2, v2 was 11 by 2. So v1 is the value matrix for head 1, v2 is the value matrix for head 2. So what we will do in this last step is essentially we take the attention weight matrix of the first head, we multiply it with the value matrix of the first head. So that gives us the context vector matrix for head 1, which is 11 by 2. And for the second head, we similarly take the attention weight matrices of the second head and we multiply it with the value vector for the second head. So that's 11 by 11 multiplied by 11 by 2. And that gives us the head 2 context matrix. So head 1 context matrix is 11 by 2 and head 2 context matrix is also 11 by 2. And now remember what we do after this point is that we have the context vector matrices from both the heads. And remember what we had discussed at the start. Once we have the context vector matrix for the head number 1, and once we have the context vector matrix for head number 2, we'll just merge these context vector matrices. And that's exactly what we do in the last step. In the last step, what we do is that we have the first head 1 context matrix, which you can say as giving us the first perspective, that is perspective 1. And we have the head, sorry, this should be head 2. So we have the head 2 context matrix, and that essentially gives us the perspective 2. And when you merge these context vector matrices, you will have the final context vector matrix, which is of the size of 11 by 4. So to the left side of this is my first head, to the right side of this is my second head. So ultimately, when I merge the results from both the heads together, I'll have the context vector of size 11 by 4. And remember, now if you had just done a single head attention, if you had just done a single head attention without splitting into two heads, the output dimension is 4, right? So you would have also got the same context vector matrix size 11 by 4, but it would not have consisted of two perspectives. In a single head, if you had just used a single head, there also you would have gotten the same context vector matrix of 11 by 4. But there, the whole thing would have been just one perspective. But now the advantage here is that the final size remains the same, but it consists of two perspectives. The first perspective given by my first head, which I'm calling P1, and the second perspective given by my second head, which is called as P2. So we have just extracted more information from my text. Of course, the disadvantage of this is that for extracting each perspective, we have only two dimensions to play with now. That's the drawback. Whereas here we had essentially four dimensions for each perspective, right? But now we have a reduced number of dimensions to play with for each perspective. That's the drawback for multi-head attention. The main drawback is that the dimension size for each head reduces, right? As you see over here, the dimension for each head is effectively reduced because we have to split the whole query weight matrix, key weight matrix, and value weight matrix into two. So the dimension size for each head is reduced. So the amount of information we can capture is a bit reduced, but the number of perspectives we can capture is increased. So each head captures more perspective. So the way I think about it is like divide and conquer. Instead of conquering the whole sentence at once, you divide into different parts and then let each part conquer some different perspective. That's the simplest way I like to think about multi-head attention. So this whole step-by-step procedure which we saw, let's recap it quickly. We start with the input embedding matrix. The artist painted the portrait of a woman with a brush. And I've deliberately started with a sentence here which can be looked at from different perspectives, correct? So what we do here is that we start with the input embedding matrix, and when we multiply it with the trainable query key and the value matrix, we split these trainable weight matrices into two parts. So we fix the output dimension equal to 4 and we decide the number of heads. So since we have two heads here, each head will essentially get two dimensions. That's called as the head dimension, which is the d out 4 divided by the number of heads, which is equal to 2. So WQ1 is 8 by 2, WQ2 is 8 by 2, etc. So we have this. These are the query key and the value trainable weight matrices for head number 1, and these are the trainable query key and the value weight matrices for head number 2. All right. So once we have these multiple copies of WQ, WK, and WV, naturally it leads to multiple copies of query key and value. So head 1 has one copy of QKV, which is Q1, K1, and V1, and head 2 has another copy of QKV, that's Q2, K2, and V2. Then what we do is that for Q1 and K1, we have the first attention scores matrix. For Q2 and K2, we have the second attention scores matrix. The first attention scores matrix is from head 1, second attention scores matrix is from head 2. Why do we have two attention score matrices? Well, each head might be capturing a different perspective, such as maybe the first head might be capturing this perspective, maybe the second head might be capturing this perspective, etc. So each head might be capturing different perspective, and that's why we have two uh, attention scores matrix here. In my view, this part is the most important step because here we see that each attention scores matrix captures a different perspective, and that's the whole advantage of the multi-head attention mechanism. And then after that we follow similar steps which we had seen for self attention. We then take the attention score matrix, scale it by square root of keys dimension, apply softmax, apply causal attention, which means we mask out all elements above the diagonal in the attention weights to be 0, and then if needed we can apply dropout to improve the generalization performance or to prevent overfitting. So until this point, we have the attention weights which have been calculated. And then what we do is we multiply the attention weights for every head into the value vector for that head, V1 and V2. And then we get the context vector matrix for head number 1, context vector matrix for head number 2. What the context vector matrix for each head represents is that Now we have 11 rows here, right? The artist painted, etc. So we go from input embedding to a context vector. So now for artist, instead of just looking at the semantic notion of artist, the context vector for artist now captures information about how this artist relates to the other tokens. That's why this matrix is much more richer than the input embedding matrix. So this is the head 1 context vector matrix and this is the head 2 context vector matrix. And in the last step, what we do is that we merge the context vector matrices for both the heads, and that leads to the final context vector matrix 11 by 4. The size of this is the same as what it would have been if we just used self attention with a single head. But the main advantage is that we have now two perspectives within this context vector matrix P1 and P2. So hopefully we'll capture richer representations in the text itself. The disadvantage is, of course, in each perspective, we now get reduced number of dimensions to play with. So the expressivity in each perspective might be reduced. But this is a trade-off which seems to work well in our favor because all the modern LLMs are based on the multi-head attention mechanism. We no LLM just has a single head. We have multiple heads so that each head can capture a different perspective. So this is the whole step-by-step procedure of how we go from the self-attention mechanism to the multi-head attention mechanism, which was the main purpose of today's lecture. Now what I want to show you is that I want to show you a very quick demonstration of how of visualization of these attention heads. So what we are going to do is that we are going to take a pre-trained large language model. We are going to take a pre-trained LLM. So this is going to be a BERT model, and it will have a bidirectional attention. So causality is not implemented. So every token will look at previous tokens and also the tokens after that. So this is pre-trained, which means it has already been optimized on a huge amount of data. What we'll do is that we'll pass our input sentence. We'll pass our input sentence to this pre-trained LLM. And what's the input sentence? The artist painted the portrait of a woman with a brush. We'll pass our input sentence to this pre-trained LLM. And then what we'll do is that we'll peek into the different attention heads and we'll see what every attention head essentially gives us. So remember that when you see the code, there will be two parameters. There will be layer and the head. So what layer essentially means is that an LLM architecture has multiple transformer blocks and each transformer block has multiple attention heads. So when we look at different layers, it means the different transformer block, and when we look at head, it means that which head we are in a particular layer. So for the purposes of demonstration, we are only going to look at layer number 3, which is essentially the third transformer block. And in this layer number 3, we are going to look at attention head number 3 and attention head number 8. What does it mean, attention head number 3 and attention head number 8? The pre-trained LLM which we are looking at will have 11 attention heads. So the output dimension is split into 11 different parts, and then every attention head will essentially get d out divided by 11. And then we are going to look at the attention weights matrix such as this for each head, and that is going to tell us that when we look at women, for example, what is prioritized by different attention heads. So let's quickly jump into the demonstration right now. So the package which I've downloaded over here is BERTWiz. And then what I'm simply doing is that I've loaded the pre-trained model over here, and I'm just showing a visualization for this sentence. The artist painted the portrait of a woman with a brush. And first I want to show you for layer number 3, and we'll see for layer number 3 and essentially head number 3. So if you go into layer number 3 and head number 3, and if you hover onto women, let's see. So if you hover onto women, you will see that the maximum attention is given to brush. If you see on the right hand side, the maximum attention, if you trace this line, you'll see that the maximum attention is given to brush. And we can also confirm this. So in this code, I've essentially plotted the different attention scores which are given for women, and I've taken a screenshot over here. So if you look at layer 3 and head number 3, and if you take the query as women, here you can plot the tokens for which the maximum attention weight is given. So the maximum attention weight or score is given to brush for layer 3 and head 3. But now let's go to layer 3 and head number 8. So if I go to layer 3 and head number 8 right now, you'll see that when you see woman, the maximum attention is now given to portrait. And that is again confirmed over here. If you see layer number 3 and head number 8, maximum attention is given to portrait. So this might indicate that here the attention of the woman is given to brush, right? So that might mean that here we have this second visualization. Um, so let me take a oops. Um, After this loads, let me take a screenshot of that second visualization. Yeah. So it seems that the attention between woman and brush is the maximum, right? So it seems that head number 3, which we saw over here, thinks of this interpretation or this perspective, because it seems in the second perspective the woman holds a brush in her hand, and the attention between woman and brush is the maximum in this head. Whereas if you look at head number 8, the attention between woman and brush is very low. So it seems that this head has recognized that maybe the woman is not holding the brush, but the woman is just present in the portrait. So it might mean that this second head thinks that this perspective is more strong. So it maybe decodes this perspective. So here you can see this is the direct proof that a pre-trained transformer or a pre-trained LLM rather has different attention heads, and each attention head can essentially uncover a different meaning. The head number 3, which we saw over here, uncovers this meaning that maybe the woman holds a brush in her hand, whereas head number 8 uncovers this meaning that maybe it's just a portrait of a woman and the woman might not be holding a brush, but the artist might just be painting the portrait of a woman. So in this hands-on demonstration, we just saw that different attention heads can capture different perspectives, and that's the whole aim or the whole purpose of the multi-head attention mechanism. I hope I have been able to explain what's the intuitive need that we need to go from the self-attention mechanism to the multi-head attention mechanism. This lecture was specifically dedicated to introducing the intuition behind multi-head attention mechanism. In the next lecture, what we are going to do is we are going to do actual calculation using mathematical numbers. So we are going to start with a given sentence. We are going to assume some numbers and we are going to apply multi-head attention in practice. But I did not want to directly jump to this lecture without giving you an intuition for why we move from self-attention mechanism to multi-head attention mechanism. This is the core building block of why LLMs work, and it's also the core building block which DeepSeek figured out that we need to modify this block itself to make it a bit better. So although multi-head attention has a lot of advantages, it does have some disadvantages in terms of storage space and computational efficiency, which are mitigated or reduced by key value cache and further reduced by multi-head latent attention. So that's why we have this important milestone in our way. We cannot understand KV cache or multi-head latent attention without understanding multi-head attention itself. So after the next lecture, we'll directly move to key value cache and then a multi-head latent attention, which is the first fundamental innovation in DeepSeek. So stay tuned till that time. And I hope you are making notes alongside. These lectures are a bit dense and I'm deliberately making them a bit longer so that everything is explained to you. This won't be a lecture series of 2 to 3 lectures. I'm planning it to make it 35 to 40 videos of lecture series so that ultimately you really understand the nuts and bolts of how DeepSeek is constructed. But to go to that stage, it's important for us to be on the same page with the building blocks. Thanks a lot, everyone, and I look forward to seeing you in the next lecture.